Good afternoon, and welcome to the Control of Complex Systems Initiatives lecture series. I have the pleasure of introducing our speaker today, John McDonald, who will speak on grid modernization, technology advancements beyond smart grid. Mr. McDonald is an award-winning industry leader, technical expert, educator, and speaker who currently serves as the Smart Grid Business Development Leader for GE Power's Grid Solutions business. John has served on the Board of Governors of the IEEE Standards Association, chaired the Smart Grid Interoperability Panel's governing board, and is a member of the NIST Smart Grid Advisory Committee. He also has served as the president of the IEEE Power and Energy Society and on the IEEE Board of Directors. He holds a BSEE degree and MSEE degree in power engineering from Purdue University and an MBA in finance from the University of California, Berkeley. He's a life fellow of IEEE and has published 80 articles and papers and co-authored 4 books. So with that, I'll introduce John McDonald. Thank you.
Well, it's great to be here. Thanks, Michael. Thanks, Sherry, and Mark Rice for reaching out to me originally. It's my first time at PNNL. So what I realized when I was planning a trip here was how many people here I know that I see bit by bit in different industry meetings, but now I put them all together here. And I said, wow, I know a lot of people here over the years. And it's great to come and see everybody. So originally I gave a number of different topics to the folks here and said, which ones of these should I talk about? And they said, we like all of them, okay? So I have a little bit of a number of topics, okay? And that's what I'm going to go over. So I've done a number of things in the industry, so there'll be a perspective on technology, what we talk about from a lot of years of experience and living through a lot of the changes that we're going to talk about. My next slide has a few things about myself, my background. I put a couple pictures in here for Ron, particularly Ron Melton. Ron and I love to exchange our training regimens, and this was just from a couple weeks ago. That's my trainer, who was a pro football wide receiver for Georgia Tech and a pro football player for the Bears and the Falcons. We've trained one-on-one for 6.5 years, and we both took second in our age group in a 5K race a couple weeks ago. And my son, when he graduated from Duke in the MBA program, there's a very famous 5K trail at Duke University that my dream was to run it with my son before he graduated. And so we did it one morning. But so I have 43 years working full-time in smart grid, 46 years active in IEEE and IEEE PES. So to be a life member, you have to be old, right? And so life means you're old. I love to mentor young professionals. I've actually been reverse mentored at GE, and a Computer World magazine wrote an article on a young professional who reverse mentored me for 3 years from our IT leadership program. If Carl Imhoff was here, we exchanged, Carl and I with Boy Scouts, we're very involved with Boy Scouts. My son and I are Eagle Scouts, and the best part about being on the board of the Atlanta Area Council is I started an Explorer post at GE 4 years ago. And I have 40 high school boys and girls that come to GE one night a month during the school year. And I have different programs on science, technology, engineering, and math. And really impacted many of these kids to study engineering and computer science when they go to the university and think about working in the energy field. There's an article on my Explorer post in T&D World magazine. So Rick Bush from T&D World liked this so much that we wrote an article for T&D. And then my 2 grandchildren live 3 miles from me, so I spent a lot of time spoiling my 2 grandchildren. So I'm going to touch on these topics: key trends, concepts, solutions, microgrids, DMS, data types, IT/OT, convergence, big data, standards, and lessons learned. Okay, I'll finish with that. So the reason I start with this is So many companies today and people in companies, we're making business decisions for our companies without really knowing what's happening in the world around us, okay? You can't be 100% internally focused. You have to have a balance between internal and external focus. You could be making decisions, technology development, where a new standard is being worked on in the IEEE or IEC and it's published, and all of a sudden your technology is obsolete, right? So you really need to know what's happening in the world around you. Key industry societal trends. I say there needs to be a balance between internal and external focus. Organizations should encourage their folks to go out, write standards, right, present papers, and see what's happening outside of the company, outside of the organization. So a couple things. We're transitioning from devices and systems to holistic solutions. For many years, we focused on microprocessor-based device, right? A group I led in the substations committee, the IEEE-PS, we coined the term IED in the late 80s, early 90s when we updated the SCADA standard, which is C37.1. We're focused on microprocessor-based devices with two-way communications or systems like EMS, right, for generation transmission, or DMS for distribution. But now we're looking at the big picture, yeah? Don't just look at individual control systems like in a building we talked about this morning, but look at the coordination across all of those in the whole building, right? How can we optimize that? Or don't just look at the substation, but look at the grid edge, the substation, and the control center, and how do we optimize that whole integrated solution? I'm going to show you examples of 6 of these solutions. Success is not just technology, even though we love technology, but standards is extremely important. That's one of the lessons we learned after 18 months of deploying smart grid projects. And policy. Policy is the strongest driver to encourage investment in technology. So you can't ignore policy. That's why I've spent a lot of time with the Public Service Commission of Ohio recently. They have a Power Forward program going on to modernize the grid in Ohio. In April, we helped them with the glimpse of the future in grid modernization in July. Jeff Taft was there both in April and July. In July, we talked about what technology do we need to enable that glimpse of the future, okay? And then the last step is what changes in policy do we need so that'll be real, okay? So, and then I've spent time with Rhode Island, with the Public Utility Commission of Rhode Island. Grid flexibility and self-healing is very important. You know, on the distribution system, once the logic is tested, why don't we close the loop on the logic and let fault detection, isolation, restoration, or FLISR, right, whatever you want to call it, do its thing with no human in the loop. You know, especially upstream restoration. We can take the human out of the loop. Many utilities want a human in the loop with downstream restoration because it's much more complex, can be much more complex, okay? But if we keep a human in the loop, we typically exceed the 5-minute threshold for SAIDI and SAFE, right? So the customers on the healthy sections of the feeders count against us with reliability, okay? Because a dispatcher just can't react fast enough in an emergency situation in less than 5 minutes. So let's work more on self-healing, and there's a couple things there. One is, once we have a confidence in a logic, let's close the loop on the logic. If you think about it with generation and transmission, we've closed the loop on automatic generation control logic in an EMS for decades, right? We let an EMS send 100 millisecond, 200 millisecond pulses to a power plant and move large generators with no human in the loop every 4 seconds, okay? So it's distributing the intelligence and having confidence in the logic to close the loop. Resiliency. Power system, the resiliency of the grid is huge, so much so that it's caused us now, instead of thinking of microgrids only in niche applications like rural villages, university campuses, and military bases, to look at, every utility now is looking at their grid from a point of view, how can I break this up into microgrids? Because if I have a series of microgrids instead of one homogeneous grid, I can have more resiliency, have more flexibility. Right? ComEd has, 5 or 6 microgrid projects going on in the Chicago area. Why is this important? A couple of years ago at GE, we hired Gallup, and we did a survey of thousands of utility customers in the United States. And we said, how many of you would be willing to pay $10 more per month on your electric bill if the extra money went to making the grid more resilient? And 41% east of the Mississippi said yes, and 34% west of the Mississippi. Much higher than what we thought. And the reason east of the Mississippi is higher is because they've experienced 3 times the outages of those west of the Mississippi. Okay, but that's a significant number of people, of customers, who are concerned about resiliency. And then we have much more data, but we're also putting more sensors on the grid, right? Jeff Taft calls it an observability strategy. Utilities need an observability strategy today. You know, what sensors do you need? Where should they be placed, right? Because the placement should be optimized. And I don't want to put more out there than I need, right? So what's my strategy? And then at the EMS user group meeting a year ago, where I presented the consensus of the big EMS vendors was that very soon the platform of EMS systems of the future will be totally cloud-based. Okay, so we're moving much more to the cloud. I wrote an article probably 4 years ago called "How Can We Use Social Media to Accelerate the Restoration of Electricity After an Outage?" Okay, and I showed how we can enable customers to use Twitter and tweet outage information. And I showed in the article how I can parse the tweet and extract information with no human in the loop and put that directly into the outage management system. Know what's important in that tweet from an outage point of view and integrate that into the OMS, okay? And we've been doing that, okay? We can't use the landline phone system anymore with caller ID. How many millennials have landline phones, right? So we need, in the same survey we did at GE, we asked what's your preferred way to interact with your utility? 70% said through social media. 70% of all the people we polled, okay? So we need to, from an industry point of view, we need to think about that. And then we'll talk about convergence of the information technology part of the utility and the operation side, okay? So, you know, what's important is just that, is the integration of the electrical and information infrastructures. And I've been doing projects in this area for probably 20 years. And through the next hour, I'm going to mention articles I've written, you know, or maybe books I've co-authored. If you want copies of any of those articles, just make a list and send me an email, okay? Because I have PDFs of all of these. But I wrote an article about a project at LADWP in the mid-2000s about bringing IT and OT together and doing an enterprise data management project, okay? And the problem, or the challenge is we have a lot of valuable information on the operations side that we need to bring over to the corporate side so that information could be shared with business groups in the utility, okay? Not just siloed on the operations side. I'll give you some specific examples in a little bit. So, 4 things here. The first 2 are ones that we're familiar with and we've been working on: reliability, performance, productivity, energy efficiencies, the environment. But these last 2 are new to us with Smart Grid. Empower consumers to manage their energy usage and save money without compromising their lifestyle. This is not doing direct load control, but it's actually giving the end-use customer tools and education so they can manage their own energy use without compromising their lifestyle. So what we found with Smart Grid was we have a new stakeholder, and it's the end-use customer, which we really never really engaged with, right, our industry. Right? Reading a meter once a month and sending a bill is not customer engagement. So you can't put PG&E and other utilities learned early on, you can't put smart meters on your customers' homes without spending some time with them, engaging with them, and making sure they understand what's the capability that you're providing them, right? So 7.5 years ago, we formed a new organization in the industry called the Smart Grid Consumer Collaborative. Over 100 members, and all the dues money, we focus on research and education on the consumer side of smart grid. What's the value proposition of the end-use customer? Not the value proposition to the utility, but to the end-use customer. And then optimize renewable energy integration, okay, is a real challenge. We'll talk more about that. But I like to call this the smarter grid, because many of us have been working in this area for not just years, but decades. So the main thing with smart grid was, hey, this isn't the first time we've been adding intelligence to the grid. Many of us have been doing it for a long time. What is it that we're doing new, okay? So you can see green is new and gray is old. So halfway through voltage control to the right is new, because we've been doing voltage control I was doing it in SCADA with SCADA systems in the 70s, especially for co-ops, electric co-op utilities. The difference now is we're integrating voltage control with reactive power control, right? Integrated volt-var control. The line is halfway here with sensors, and to the right, much more focused today on distribution, both DMS as well as feeder automation and smart meters. And we're putting more sensors right out onto the grid. This example is a sensor that I can put on a transformer, and it can monitor in real time the oil of the main tank and look for up to 9 different gases dissolved in the oil. Okay, in the presence of, if I see ethylene or I see acetylene, each of those gases is a specific failure mode that's occurring in the transformer. Of course, then I look at the rate, right, the rate of change. How bad is this? So a lot of work is going on with asset performance management, utilities calculating asset health indices, and now looking at fleet management across transformers. So you have a $2 million asset for maybe $20,000 or $30,000, you can know the health of that multi-million-dollar asset on a continuous basis. Makes a lot of sense because the average age of a transformer in the US today is over 42 years old. Okay? And then these are different solutions up on top. So 10 years ago, actually around as we were leading to 2009 actually, we knew that at GE, we knew that billions of dollars would be available to utilities, right, and a 50% matching with the ARRA program to deploy smart grid projects. So we knew as a vendor, there would be money available. The question was, what would utilities be looking for? We want to make sure, do we have the right things? And as I said, integrated solutions as opposed to components, right? So we studied this. We actually ranked the 51 public service jurisdictions in the US, which is 50 states and the District of Columbia, ranked those in terms of which ones were the most supportive with their utilities in their states for smart grid investment, okay? And then which of the 200 IOU utilities we had relationships with at GE, and they had some GE equipment. Cross-reference that, I came up with 38 utilities that we talked to the CEOs and the executive staff, got a lot of information, processed it, and we said, these 6 integrated solutions have the strongest business cases, and let's focus on these in terms of the money that's available from utilities. Asset optimization, the first step here is transformers. Now we're focused on switchgear, right? Circuit breakers. And third will probably be battery systems. If the battery goes out in the substation, your relaying is inoperative, right? So battery monitoring systems, and there's standardization work going on in the IEEE that says we're not just only interested in the voltage of these battery monitoring systems, but there's a lot of other metrics that we're interested in terms of the health of that integrated system. So there's standardization work going on by a group in the PES, IEEE PS, in terms of what are those metrics that we need from a battery monitoring system. Different levels of assets. Second is demand optimization. Third is smart metering and two-way communications. In the beginning of smart grid, there was so much of this that many people thought smart grid meant smart metering and vice versa, right? I said, no, 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 smart grid is much more than smart metering, but that's all you heard about in the early days was smart metering projects. The biggest focus today is right here, distribution optimization. The consensus in the industry is for every dollar invested in distribution optimization, the return is $5 to $6 back. So the benefit to cost ratio is 5 to 6 to 1 with short payback periods. Next is transmission optimization. A lot of work going on here with synchrophasers, right, and how we can use synchrophaser information. And then lastly is the workforce and engineering design optimization. PricewaterhouseCoopers had a report not long ago that said in the energy industry in the U.S., 40% of the employees, not just engineers, but employees, and 60% of the executives will retire in the next 5 years. So we really have to look at the workforce and say, we're going to lose a lot of experience, and so much of what we do is not a science, but it's an art. There's a big difference between a science. If it's a science, I can read a book and I can do it. If it's an art, I need to read the book, but then I need to spend time with experienced people and learn how to apply the stuff, right? And that takes time. And so we're going to lose that experience. In fact, when I became president of the IEEE Power and Energy Society, the average age of the PES member was 50, and the average age of the IEEE member was 42 at that time. So we changed the name of the society from Power Engineering to Power and Energy. And just having energy in the name and the programs we've done have brought a lot of young professionals. So the PES now is the second largest society of all of IEEE, where we used to be the third, grown substantially. So these are integrated solutions. Let's take these and translate these into a technology map, okay? So they're color-coded, and we can just, for time, we can just look at light blue boxes, which is distribution. And you can see there's light blue boxes in the office and the control center, substation, and out on the feeders, right? These are software applications on a distribution management system. These are the systems here. Substations, we can run applications. We can distribute the intelligence down at the substation level. And then, of course, out on the feeders. I need sectionalizing devices here to support the logic here for fault detection, isolation, restoration. And I need voltage regulators and capacitor banks here to support the integrated VOLVAR control logic, which could be here or it could be here, right? Okay? So think about this from a standards point of view, interoperability. These light blue boxes, many of these are from different vendors, right? And I need to make sure they communicate with each other and exchange information with each other. And if you've ever done a project like this, all the vendors will say, yeah, I've built DNP3 communications protocol into my product, and you hook them up for the first time, and many of them don't talk successfully to each other, okay? So standards, I mean, think of the integrated solution, equipment from different vendors, and a challenge with interoperability. Now, what's very important, and this slide came from a workshop I presented at NREL a couple of years ago on advanced distribution management systems. We had 3 vendor perspectives and 3 utility perspectives on advanced distribution management systems. And the consensus was that when a utility embarks on buying a new ADMS, 30% of the cost of the project is the ADMS from the vendor, and 70% of the cost of the project is the integration cost to properly integrate that system with all the other systems and devices at the utility. And a measure of the resiliency of that utility's grid is directly proportional to how well they've done that integration, okay? For instance, smart meters not only give me meter readings, but I can ping certain meters at the ends of certain feeders to get voltage that I put in the network model of the DMS. So if I don't have a smart meter on certain feeders, I need to add end-of-line voltage sensors with two-way communications, because I have an ANSI standard that says the voltage at the customer's premise must be 120 plus or minus 5%. And if I'm down near 114 volts on certain feeders, I need to know that, what that margin is. Also, the meters give me last gasp communication, right? There's a capacitor in there that when the meter's energized, there's enough energy then in that cap that when there's an outage, I have enough energy for one last communication. So what's nice is I know all the customers that have an outage, when it occurred, I put that right into the outage management system, right? The geographic information system is the reference system for the network model for the OMS and DMS. About 15 years ago, we started taking all the status changes from the DMS, from the SCADA system for distribution, and making sure we tied those into the outage management system. Because the OMS has the network model, knows which customers are connected to which feeders, and if it knows the status change that maybe a distribution feeder breaker tripped, that one piece of information tells the OMS which customers are on that feeder, and now they're without electricity, right? And then we talked about customers. Let's move from the caller ID phone call system and let's empower customers with social media, right? You know, for instance, where I live in Atlanta and I buy power from Georgia Power, instead of my home phone number and caller ID, Georgia Power says, John, what's your Twitter handle? I'll put that in your customer records, so whenever I receive a tweet from you, I know who it's from and what your property address is, right, through my Twitter handle. And the Twitter handles of all my family members, right? So I think one of the things that not only California required this, but I really think all public service commissions should have required this. This was an assembly bill in California some years ago that required the 3 IOUs in California to holistically, across their whole utility, to put a smart grid strategy together, roadmap, and not just siloed by group, but across the whole utility. What are the key programs you're going to focus on? What's your timeline? What projects are you going to do? How much money are you going to invest? In San Diego Gas, I worked with San Diego Gas and Electric, guys like Lee Cravat at the time, and who was leading Smart Grid to help them with this. And they said there's 9 key programs that we want to focus on, and we're going to estimate about $3.5 billion in 9 programs through 2020. Many utilities haven't done this. And if you haven't done it, you're doing a number of different smart grid projects, but they're not aligned with any corporate strategy, right? Which means that there might not be a follow-on step to a project. It may be a stranded equipment, right? There's no plan, follow-on plan, because there's no overall corporate strategy. I like the fact that the California Public Utility Commission required their utilities to do this, okay? So let's look at microgrids. Well, distributed generation in general, you know, renewables, we can interface at the transmission, distribution, or the end user level. And I think, you know, we all know that when we designed the distribution system originally, it was really for flow of electricity from source to load only in one direction. Now we start putting distributed generation, and now we have two-way power flow, and I'll talk about some of the voltage regulation concerns. So what are some of the challenges? Open circuit overvoltage due to unintentional islanding, protection ratings now that don't match fault currents. When we did the short circuit study, we looked at the source side contribution only. Now we have load side contributions, so our protection ratings may not be accurate, but the contribution to the fault from the load side, because these are intermittent generators, varies, right? So that complicates it even further. How do we establish the protection ratings if we have sizable amount of DG downstream? And I'll talk more about the voltage regulation equipment. So this is the first microgrid project we did at GE. This is at British Columbia in a rural village that had fuel cells, PV panels, low-head hydro, the traditional diesel, both industrial and residential load. And we took a relay and added logic to the relay to be a microgrid controller to make sure that the load was satisfied on a continuous basis, but to optimize the use of the fuel cells, the PV panels, and the hydro, and minimize the use of the diesel, right? And then high-speed, you know, communications here. Each of these blue boxes is communications to tie everything together, okay? As I said, now we're looking at microgrids not just for military bases and university campuses and rural villages, but many utilities now are looking at those in terms of, can it help the resiliency of the grid? I think one of the best projects here that I've seen in person is the one at the Philadelphia Navy Yard with multiple microgrids, part of an economic development for an old Navy yard. And this was actually done originally by Alstom, and then Alstom became part of GE. But there's a microgrid center of excellence there that you can see. We provided a distribution management system, so there's a network operations center with a video projection screens, you know, like a control room, and then different microgrid projects that you can tour, okay? And it works closely with PJM, okay, and PICO, okay, as well as working with Penn State and some DOE funding. So here's Grid Lab D, which is part of this from PNNL, DMS SCADA system I mentioned, and then microgrid control systems for each of the microgrids. Okay. Some of the challenges, though, you know, is bridging the intermittency. Of course, energy storage is one example. Another one would be, you know, using fast start thermal generation. So many generation vendors now have focused on how can we get typically natural gas fired generation that we can, you know, start up more quickly and it can react more quickly to changes in frequency. You might have seen a couple months ago, GE announced a combination of a 50 megawatt natural gas fired generator with a 10 megawatt lithium battery in a hybrid configuration with software that optimizes the operation of that solution with the grid conditions. Okay, so the intermittency drops, you know, the battery can kick in immediately, and this fast start takes a couple minutes to get up to speed, and then the generator can kick in and the batteries go down. The generator can keep the batteries charged, and it's a very intelligent system that optimizes the use of those resources with the changing grid conditions. This is a family of new devices that we call grid edge controllers on the low voltage network, right? So in areas where we have a high penetration of photovoltaic panels on homes, we have a lot of volatility on that low voltage network when you have high penetration, okay? And we need to address that volatility on the low voltage network. We don't want it to propagate up into the grid. And so Verentech is one company that has these low voltage network dynamic grid edge controllers. They're installed in many utilities in the US and Mexico that are one level up in the hierarchy from a control point of view. So the lowest level, you have the inverters that couple the renewables to the grid. Next level up, you have these grid edge controllers. And they're small, they're on the low voltage network, and you put a number of these, they're not real expensive, and you put a number of these on the low voltage network, and load flow studies and simulation studies can determine how many you need and where they should be placed, okay? So these are power electronic based. So that leads into this, where this was 4 years ago. And what I was seeing in the industry, I said, you know, we traditionally have controlled the grid with mechanical controllers. Okay, think of a tap changer in the substation. Okay, and I was working with San Diego Gas and Electric. Tom Bielek, the chief engineer there with Smart Grid. Tom's great, and Lee Cravat. And I got the voltage waveforms from one of their distribution feeders that had 35% of all the homes on the one feeder had rooftop solar panels. 35%. And these were real nice homes along the Pacific Ocean. And when the marine layer of fog was over the homes in the morning, of course there was no generation, but as that fog burned off, what happened was on this feeder, it went from 0% generation to 100% generation instantaneously. What do you think happened to the voltage on that feeder, right? It spiked and then oscillated as clouds and things moved, and So what happened to the tap changer in the substation, right? The tap changer is mechanical, right? 16 positions up, 16 positions down, middle position, 33 positions, 0.5% volts between taps, but it's mechanical, right? So this thing, before PV panels were installed on any homes, it was designed with a 35-year life and operating about 5 to 10 times per day, okay? Now with 35% penetration, it was operating 90 to 100 times per day with a lifetime of 2 years or less, okay? So I'm thinking about this, I'm thinking, wow, we need to rethink the future grid with any kind of penetration of renewables could be much more volatile. Think about control. From a control point of view, we need to think, how do we control the future grid? Mechanical means just they're going to wear out, right? It's just not feasible. So that's why I wrote this article for Power Electronics magazine. The premise was there's new applications of power electronics that we need to think about. And I can't, I go into universities to give talks and I see the power electronic researchers at the universities still doing research separate from the power system analysis folks. I'm saying, here's 3 good examples on why we need to bring this expertise together. We've looked at power electronic online tap changers. In fact, we developed a prototype at our research center. So did ABB, so did Siemens. Low voltage network dynamic grid edge controllers, power electronic based, new family of devices. And of course the smart inverter. And we're working with the California utilities with Rule 21 and what the CPUC now is required in terms of the functionality of a smart inverter and the communications of the smart inverter. This is just 3 examples. Power electronics to me is going to have much more widespread use on the grid as we go forward, particularly as renewables increases. And then the fear here of utilities is, this happened in Australia where the policymakers in Queensland passed new policy to greatly incentivize homeowners to put PV panels on their roof. And so many did so quickly, the utilities weren't prepared. And all of a sudden, the utilities are fearing that the customer is saying, why do I need the utility anymore? I'm generating my own electricity. And so these homeowners say, I'm disconnecting from the utility. I'm self-sufficient. And the utilities say, wait a minute, as a mass of these customers do this, my revenues go down, and I may need to raise rates, right, to account for that. And of course, that's the death spiral. You raise rates, then more customers leave, and then eventually you don't have enough customers to be viable, okay? That's called the death spiral. There's a good article in Intelligent Utility magazine in December of 2013 about that. So we've learned a lot of lessons with renewables. There's impediments like lack of transmission, lack of control area cooperation, across control areas, unobservable DGs. We have distributed generation out there, but we have no observable. We don't know. There's no measurements, no sensors, no measurements coming back. And then enablers, though, too. Better forecasting, a thermal fleet, higher quick starts, deeper turn down, faster ramps. There's more spatial diversity, which helps us with renewables. And so there's impediments and enablers. And then, you guys have worked closely with GE's Energy Consulting Group that does the power system studies. And this is just a sampling of some of the wind studies and projects. And some of these may have been done with, I know there's some with NREL here, with PNNL. So, we can do DMS applications at the substation level. We're also looking at how far down into the grid edge can we put these. But this is the centralized model here, where we have the SCADA platform, then we have the applications here. This is the geographic information system for the network model, and this is the substation and feeder devices, right? So this is your ADMS, basically, here. This takes some time to implement. So if I was a utility and I was starting on this, I would put logic right away in my substation, and that's to do fault detection, isolation, restoration, as well as VOLVAR control, because I could realize benefits quickly at the substation level. And while I'm doing that, I would begin implementation of a centralized approach. And the reason is the ultimate architecture for any utility is a hybrid architecture that's a combination of centralized and distributed. When I can, I'm going to make decisions downstream and then report out after the fact upstream what I did. And in some cases where it's a very complicated situation, I need to see more of the grid, I'll need to do it upstream because I can see the grid, the whole grid from upstream. But I'm not throwing anything away. Okay, and I would say the ultimate architecture even further is centralized, substation, and grid edge. I see we're going to put more intelligence at the edge of the grid in terms of not only information, but decision making at the edge of the grid. So we have grid edge, substation, all in a hierarchy, all working in a hybrid architecture. Okay, so when we do another guy and I do a one-day tutorial on advanced distribution management systems. We did it at Distributech, and we're doing it again. We did it at the general meeting, PES general meeting, just recently, and in Chicago. And we'll be doing it again at Distributech and at PES meetings next year. But I like to think of applications in three different areas. One would be real time. So these are online that the dispatchers use. Okay, topology processing, VOLVAR control, fault detection, isolation, restoration, state estimator, and load estimation. The analytical applications, which I can do on demand. I classify this one as both on demand and online, because I would want to, if I was an operator, I'd want a power flow tool I could use online. And then the rest of these are more study or on demand. And then some ancillary applications the utilities have. Okay? So the timing of these, how often they run is very important, but there's really three groups that we need to look at. Now, this is very important. I went through this with the Rhode Island Commission and National Grid because utilities with automation, it's not an all or nothing approach. As a researcher or as a vendor, if I want to be successful with a customer, I can't require that customer to go from where they are today to the ultimate configuration in one step, right? Typically, they can't afford it. And secondly, they probably don't have the resources to implement that quickly. So I need to break it down into milestones, but each milestone must have benefits associated with it. So I said, for fault detection, isolation, restoration, there's different levels of automation. There's different levels. It's not an all or nothing approach. It's not discrete, but it's multi-step. I can do manual control and legacy methods. Then I can go big positive step over manual. I can do automation and visualization, and I can be the ultimate digitally enabled. And these are the steps, okay? What's the outcomes of each of those steps? Well, at the base level, manual control and legacy methods, I'm manually operating a network and I have a static view of the network configuration. Then I go to circuit reclosers, trouble calls and AMI with customer status, remote control and monitoring with SCADA, and I have 28% improvement with customer minutes interrupted. Okay? So that's a significant benefit. Take another step and I do outage management, prediction analysis, network visualization tools, and distribution automation with power flow analysis. 43% improvement over with lower customer minutes interrupted. And then digitally enabled, I have network optimization and asset performance management and outage analytics and greater than 50% improvement. Okay? So this is what public service commissions, this is what we need. You know, we need to show that in the real world, a stair step to get to the ultimate is what's needed. I can afford that with my budget process, and I can afford that with the resources that I have available, right? Here's another important point. I don't have to implement fault detection, isolation, restoration logic on every single feeder, okay? I study my feeders, and in this example, this utility that we studied, there were 200 circuits, or no, there were 856 circuits. Okay, so initially you say, well, I need to implement fault detection, isolation, restoration on 856 circuits. Well, it turns out you study those, 23% of those circuits, about 200 circuits, are responsible for 71% of the total outage minutes. Okay? Be smart about what we're doing. Help the customer, okay, so that you're only spending money here, right, and you're getting the biggest bang for the buck. So I need to implement the technology on 200 circuits, but I'm covering 71% of the total outage minutes. Okay? So I wrote an article in 2003 in IEEE Power and Energy magazine, and I introduced the concept of operational and non-operational data. Because I was looking at these new IEDs, these new devices, and I said, we can't manage these as if all the data is the same. It isn't. Okay? We typically only focused on the data that went to the control center, to the operators, but IED vendors, the sexiness of an IED is not the operational data. That's the standard stuff. It's the non-operational data. It's the digitized waveforms, sequence of events reports. It's the stuff that the power quality group or the asset management group, right, the planning engineers that they could use. So I said, okay, operational data is the stuff that the operators need in the control center, real-time status, performance, loading. It's a time series of points at the scan rate of the SCADA master, okay? Circuit breaker status, line current, bus voltages. The non-op data, the primary user is someone other than the system operator. You know, digital fault recorder records, circuit breaker contact wear, dissolved gas and oil. And the sexiness of these devices, the differentiator across vendors, is right here. It's not the operational data, it's this stuff, okay? Beckwith comes out with a new capacitor control, and it has harmonic information inside the capacitor control, which we had never had before, okay? That's the differentiator. How can we take advantage of that? If that has value to us at the utility, how do we take advantage of it? We need to manage the data. There's different types of data, okay? So operational data is typically time sequenced, typically real time or near real time, and we typically extract that with standard protocols because it's a SCADA master. Non-operational data is typically, it could be a point or a file, mostly historical, and if it's a file, we may need the vendor's proprietary format, like an ASCII protocol to extract the file, okay? So how do we manage this? Well, one of the things in the industry is taking advantage of the wave called Internet of Things, right? And we're bringing together intelligent machines with big data and analytics and people at work. And the connectivity is increasing, right, such that we'll have more data more readily available to us. How do we take advantage of that? And we've, you know, it's the next productivity revolution, and we've looked at the savings of that. And GE formed a GE Digital business, a separate business focused on this. And we have GE Digital people in every single GE business that's looking internally at the business and how can the business do things better with implementing with the connectivity and readily available information, as well as the products we develop for customers, okay? One of the offshoots of this is new analytics. How can we analyze data in different ways to provide new value streams to customers. Okay, we haven't been creative enough as an industry. If I ask you to benchmark best practices, you typically will benchmark within your own industry. Okay, and that's not being very creative. If you want to benchmark outside the industry and learn from others outside the industry. Okay, when we had the global federation. We had an event every December, the Gridwise Alliance in Washington, D.C., and I did an event on customer engagement, and I brought in the CEO of Procter & Gamble to teach us how to do customer engagement, our industry, because we didn't know what customer engagement was, but here's a company with $26 billion brands, right? Each brand brings in over $1 billion a year. Teach us how to do customer engagement, okay? Think outside our industry. So we've looked at more insight in metering information, outage, reliability, renewables, and as I said, the end-use customer segmentation. Not all customers are the same. So when we do programs for end-use customers, we've defined 5 different segments of customers. So different characteristics and different price points. So here's the situation today with data is each group in a utility has their own systems, their own devices, and their own repositories, right? Databases. And they really don't share. When I was consulting, I found the same value from the same relay in 4 different databases in the utility. Each of those 4 groups went across the firewall, right, into a secure system in the substation to get that data. I'm thinking we should do that once, bring it across the firewall, right, to some corporate network repository. And if others need it, let's do it on the corporate side. But it's because everything's siloed, you know. A relay has I2T information on the breaker it's connected to, right? The relay, I can't tell you how many times I saw this where the protection group bought the relay, put it in a substation, connected to the breaker. It has I2T information, the operations counter information on the breaker was sitting in the device, okay? The maintenance group never received it because the relay group didn't care about it. They cared about protecting the grid. And they didn't reach out to other groups, right? So here's what really kills me is there's 52,000 distribution substations in the U.S. Only 2/3 of those today have any kind of automation installed at distribution. We have an observability issue. What really kills me is of the 2/3 that have automation installed, half of those automation devices are operating standalone. Even though they have two-way communication capability and valuable information inside, they're operating like an electromechanical device, a standalone device. We're not using the communications to get that data upstream, okay? This is what we want, see? A federated data mart, it's a virtual data mart that brings together all the systems, devices, and existing repositories and manages it on an enterprise level, okay? And again, I wrote I have a couple articles on this, and one is a case study from Los Angeles Department of Water and Power, from IEEE Power and Energy magazine. I wrote in 2006, if you guys are interested, okay? So the end result is we have a standard architecture so we can extract the data that we've identified has value. And here we have all the different sources of data in the enterprise, and here we have all the different business groups that could provide more value to the utility if they had that data, okay? So I'm going to wrap up here in a minute. 25 to 30 business groups in addition to the operators in the control center that need that data, okay? So this is the workshops. This is how we do it within a utility. Conduct a workshop initially to bring all the utility stakeholders up to the same level of understanding of what we're talking about. Review the data maps of all the devices, systems, and repositories. Identify the data that has value to at least one group. Create a standard IED data template. So this is a process. It's a series of steps. And then develop an enterprise data requirements matrix. What we do is we map the data points of value to the stakeholder groups that will use the data and have standard architectures. So it's not difficult to do. It just requires bringing together a number of different groups in the utility. Okay. This is preaching to the choir here for many of you, but you guys know the smart grid conceptual reference model that was done back around 2010 with 7 domains, right? So if somebody asks you, how do you, at GE we say smart grid goes from turbine to toaster, right? That's a big landscape. If I gave you a sheet of paper and said draw all of smart grid on one sheet of paper, what would it look like? Well, this is an attempt at a high level to do that. But I think what's important is to try to get through all these hundreds of standards and narrow it down to a manageable list, right? And say which, standards are important, as we said, for interoperability. But these 16 here are the ones I focus on and we should focus on. These are the fundamental standards for smart grid. And these will cover turbine to toaster here. And you don't have to consider the 100 of IEEE standards or the 100 IEC standards. These 16, we've gone through at an industry level and said these are the most important, okay? And what's really neat in being in standards work for over 30 years is knowing that there's one worldwide standard now for control center to control center communications, ICCP. There's basically 2 that are used for control center to field equipment communications, either DNP3, which is IEEE 1815, or European suppliers will use 870-5, 101, or 104. And within the field, typically IEC 61850 or maybe DNP3. So we used to have lots and lots of choices, which made it more complicated for vendors and customers. And now it's converged to a manageable. So let me finish real quickly here with lessons learned. So after 18 months of deploying smart grid projects, we actually stopped, reflected back, and said, what did we learn? What were our assumptions in the beginning? What did we learn, and what changes will we make going forward? I wrote this in an IEEE Smart Grid newsletter in July of 2011, which is on the IEEE Smart Grid portal. Okay, so first, a lot of the reality was the component technology in many integrated solutions was not as mature as advertised when we put these components together for a smart grid solution. Okay, so in many cases we had to field re-engineer or upgrade or replace components. But I say that's part of the process of the ultimate test. Eventually you got to go from the lab out to the field, and the ultimate test is the field. And so this you expect, and this is part of the process. Integration, interoperability, integrating multiple supplier products to create a solution. Just do it. Do a project yourself, and you'll see how important standards are. You'll be a believer if there's any doubt. You have to adopt and insist on standards in an open architecture. Testing. I talked about how important testing was, but what we really learned was you can't do enough testing in the lab or factory, but more importantly, you have to do end-to-end testing. Not just the substation, but substation to the head-end system, right? That was really important. Coordinating multiple suppliers within the utility was a real challenge. Managing equipment shipments and delivery. Also, working with very, very small suppliers could be a problem, because if you have problems in the field, a very, very small niche type supplier may not have the resources to help you in the field, okay? You'd be on your own. And then I think one of the most important things from a vendor point of view, we want the utility to be successful with the project. We could have the best technology in the world, but if project management wasn't effective, project could be a bust, okay? So the project managers at the utilities not only needed the responsibility, but they needed multidiscipline authority, okay? Because these projects span a number of different departments. You ever had the feeling you were given a job to do, but you didn't feel like you had the responsibility, but you didn't have the authority? So as a vendor, we make sure, we need to make sure the project manager is a hero, because that's for the success of the project. So you need to have multidiscipline authority. And then these project managers report up to a project management office. And lesson learned here was we need to build an A team of the very best, not only technical members, but project members, right? And then there needs to be a strategy. There needs to be a corporate steering committee to implement the utility strategy. And lastly, two things. One, the end-use customer is a major stakeholder, right? We have to think about the end-use customer and understand the end-use customer. That's why the Smart Grid Consumer Collaborative to me is so valuable, because that's something, I'm a grid guy, and I needed to learn more about the end-use customer. And then the importance of use cases, right? We've all, when we're embarking on anything new, we really got to scope it out, put use cases, describe the scenario, the benefits, who's involved, and business rules and assumptions, okay? So those are some, again, this is all written up in an IEEE Smart Grid newsletter that you can find on the IEEE Smart Grid portal from July of 2011. Okay, so that was a real quick overview. Thanks.
Is there a question or two for John? Harold?
It's not so much a question as a comment. A long time ago, I was working with some GE people, actually, in Schenectady. Will this work?
Oh, yeah.
Okay. I was working with some people in GE on a project on distribution automation with a guy called Fred Schweppe. And Fred, as you probably know, originated a lot of the things that have led to the smart grid.
Right.
And I was having a beer with Fred one night, and I said, Fred, we really need you. And he said, why? And I said, because you define for us where the lunatic fringe is in this business.
Right.
And I think what you've done today, John, is define where the center is. And that's something that we need as well. And I very much appreciate what you've done. Thank you.
Thanks, Harold. Thank you. Thank you.
So thanks, John. I appreciate the talk. I guess I'd be interested in maybe a little bit of a different twist. From your perspective, you know us pretty well.
Yeah.
From your perspective, what are some things that the DOE and the national labs should be more focused on than we're not doing enough of today?
Yeah, yeah. I think one, to me, one important aspect of smart grid is you need to have a strong grid before you think about smart grid. So to me, the very first step is the communications infrastructure and the IT infrastructure to support anything you're going to add. Because I kept telling utilities as a consultant, if we add stuff and your communications infrastructure, IT infrastructure doesn't support response requirements or bandwidth requirements or latency requirements, it's not going to work. So I think, communications to me is an area with utilities that I don't think they put enough focus on in terms of a truly hybrid communications infrastructure. When you go from backhaul to the last substation, you've got a lot of different wired and wireless technologies in between. And how do we make sure the utility has a robust enough infrastructure in place before we add anything new? And the IT infrastructure, how many utilities still have disconnects between their IT and OT infrastructure? To me, that's one. Second thing is to me is power electronics and the impact of the more volatile grid and from a control point of view. Future ways to control the grid. Third area would be analytics. I think we're in our infancy in analytics with respect to value propositions for utilities. I really think we could do more in benchmarking outside of our industry and being much more creative. Those are just three that come to mind.
Thanks.
Thanks, John. Thanks to
Okay.
everyone who attended.
Thank you.